This is a brief introduction to using the RadLib software. Here I have a window with GitHub open to the address. We'll first clone the repository, copy this, git clone, and then that creates a folder called RadLib, which we'll enter. And then the directory structure is as shown. There's data folder, docs, examples, and source. So the first thing to do is to build the code. There's a README file here with instructions on that. So first create a build. We're using CMake, and then we will go into the build directory and go CMake ... so standard, and then make. And if you want it to go faster, you can add the -J8 flag or J whatever. It doesn't have to be 8. And then make install. Okay, so the installation gives you this command so that you can put that in your path, so that the Python interface can find where it's going. The installation installed a new folder called installed. You can change that in the CMake lists.txt file. So if we go into the installed, the header files are in include, the library files are in lib, and the RCSLW data has new binary files that were created from text files on this machine. The RadLib code is designed to provide radiative properties for radiative heat transfer calculations that can then be used in conjunction with a radiative transport equation solver like discrete ordinates, for example. Specifically, we find absorption coefficients and weighting factors for models. The models that are currently implemented are the Planck Mean, the weighted sum of gray gas, and the rank correlated spectral line weighted sum of gray gas model, or the RCSLW model. So that was an example of the build process. If we look at this top level CMake lists.txt, you can see some of the options that are available. The code comes with is written in C++ and has a Python and a Fortran interface. So you can change these options here for building those interfaces and the examples. You can set those in the build. Oops. You can set those CMake-D build Python interface equals on. That's how you could set some of those examples. That would be the command instead of what we did, which was just CMake ... So by default, all those flags are on except for the build documentation. Documentation is built with Doxygen. And okay, so let's look at the examples that were installed. There's a C++, Fortran, and Python. So let's look at the C++. There is a simple interface.cc, simple interface with the corresponding executable, simple interface.x, and this sets a gas state, temperature, pressure, and composition, and then it computes the absorption coefficient and weight for the Planck mean, weighted sum of gray gas, and RCSLW corresponding to that. The source code loads the interface include files, header files, and then sets the state, makes some space for the outputs, and then creates a rad object. So the way the code is structured is there's a base class called rad, and then the individual models inherit from that. So we're creating a Planck mean object, a weighted sum of gray gas object, and an RCSLW object. And then they all have the same interface. This get KA is the uniform interface, and we pass in the things that are output here, the K's and the A's, and then the input properties for the temperature, pressure, soot, and composition, and then it just outputs the results. So the primary interface here is get KA. If we go up and look at the source code, C++, and look at, for example, rad.h, there are two main interface functions. One is this get KA, and the other is get KA one band, which will give you the weights and abscissas for just a single one of the gray gases. You can specify that. So back to the examples. That was the simple interface, and we have that same thing in Fortran, simple interface.fort, and in the Python 3 simple interface.py. So all three of those should be giving the same results. In the C++, there's a number of other examples. These other examples use simple ray tracing solver to solve the radiative transport equation between parallel plates. So a one-dimensional example. And those are these EX, B3, S1, etc. We can run all of them with this .run examples, and that will run through those example profiles. And of course, if you want, you can redirect that to a file and plot the results. Those results are repeated in the Python, and there we have a simple Jupyter Notebook that gives some description of what those examples are. Let that load. So it gives some links to the references and what the examples are, and then lets you run those. So for example, if we run the cell, then we can come down to, for instance, example S3, which uses a parabolic temperature profile and a parabolic water concentration profile. And outputs the results. So these will be visible, and then it also saves to a PDF file.